We introduce PatchTable, an efficient data structure for querying patches against large image datasets. Our method takes an inverted index approach, analogous to modern search engines. We first allow a modest pre-computation time to create an index that can later be queried efficiently. We index the database image by taking all patches and populating them into a high-dimensional irregular grid, which is our table. We then fill table cells that are missing patches using a fast Voronoi transform. Finally, for each patch, we compute k other nearest neighbors for that patch. This is called k-coherence. Now we can efficiently query the data structure. We want to know for each patch in the query image what is its approximate nearest neighbor in the database. We do this by first looking up a nearest neighbor in the table, which provides a good initial guess. We can then improve this initial guess by trying correspondences from the k-coherence mapping. There might be a slight error in these correspondences, so we can optionally do a small spatial search to improve them. We do all of this on a sparse grid for efficiency, and then propagate correspondences to the dense grid of all patches. We can iterate and then return the final nearest neighbor field. We now show results from our multi-image editing application. We can build a patch table from a collection of images. After this has been done, we can perform interactive editing applications, such as the stitching shown here. Notice that the bicycle was inserted from other photos in the collection. Previous approaches such as PatchMatch, TreeCan, and CSH are not as efficient on such image collections. If the result is not satisfactory, the user can quickly synthesize a new result. Next, we show an artistic video stylization application that works similar to image analogies. The algorithm is given an input video to stylize. It is also given an exemplar pair that shows the photograph before and after stylization. Here is the result of the previous method of Hashimoto et al., which takes 2 minutes per frame to render at a low resolution. Here is our result, which has improved temporal continuity and renders at multiple frames per second. In the remainder of the video, we show more artistic video stylization results. Our input video is a bicyclist riding through a forest. This is a 1024 by 576 resolution video. Here is our result for the watercolor style shown previously. This resolution renders at 1 frame per second on the CPU. Here is an oil exemplar pair. Now we show the bike video stylized with an oil effect. Note that recent methods such as Bernard et al. 2013 can obtain higher quality but require precise optical flow from a 3D animation and take 10 minutes per frame with a GPU implementation. In contrast, we focus on efficiency. For example, we calculate each output frame sequentially rather than optimizing the entire video cube. Finally, here is a challenging engraving style. And here is the bike video rendered with the engraving style. Thank you.